So it looks like we're the last stop between you and lunch, and we'll try to make sure we go as fast as possible. I'll definitely go fast for the first half of the presentation to give a lot of time for Sangjin to go through the detail of the architecture. So what is BESS? BESS is a virtual switch tailored for NAV. It's an academic project. We started definitely as an academic project through a center co-funded by Intel and AT&T and hosted at Berkeley. The lead PIs from the academic side are Professor Scott Shanker and Sylvia Ratnasamy. They have co-PI at Stanford with Nick McCune, Princeton with Jen Rexford, and CMU via Sekar. So why another virtual switch? There are a lot of virtual switches out there, right? So one of the questions we looked at, well, what are the actual performance you can achieve with virtual switches? We know OVS, at about 1 million packets per second, OVS DPDK at about 15 millions, while vanilla DPDK can achieve about 60 million packet switching per core. Right? And packet I/O is only half of the problem we see here. Right? What about flexibility? What about if you don't want to have the match action semantic? You want to add new semantic in your processing. It's very hard today to do, or it's impossible to do with OVS itself. What about stateful packet processing? Yeah, with OVS, they have access to kernel, and they can do some connection tracking. I don't know if it's possible with OVS DPDK today. You don't have access to a lot of the information. What about extensibility? Previous speaker talked about service function chaining or new protocol. It's very hard to add this in OVS today, right? And any other switches, for that matter, right? So we looked at all these features, say, hey, let's take an alternative approach, right? Let's build a switch as a directed graph, right? A data flow graph. And you saw VPP is also, a directed graph. The click modular router from MIT is also, a directed graph, right? And each module here in the graph can run arbitrary code. If you want to run, the match action semantic, you do it in one of the modules. If you want to run any other code, you'll do it also in the module, right? And everything here is programmable, not just the flow tables. Another very, very important aspect is you pay for what you use, right? So what's the flip side? Well, it's not very generic. I mean, OVS is very generic. From the get-go, you can do everything you want, right? I mean, with such a switch here, you have to define your module, maybe a specialized module to do your functionality, right? And we'll describe after, what are the modules currently present as part of BESS, right? But, between flexibility and performance, we chose to chase performance. And we try to see, how much performance we can really achieve if you have, a tailored vSwitch. Right? One of our usage model you'll see has been the telco usage model, and knowing some of what this telecom provider wanted to chase or to follow, we tried to optimize the vSwitch for some of these usage models. So BESS, is a programmable platform for vSwitch data plane, right? It's a clean state architecture, clearly with having NAV in mind. It's highly extensible and customizable. I mean, you write the module, right? You chain them together. It's readily deployable with backward compatibility, and again with extreme performance. And you'll see, some detailed performance data in the follow-up slides we'll have here. Right? We achieve, sub-microsecond latency. We can achieve 40 gig line rate with 2 cores at 64-byte packet size. Right? And it's about 4 times faster than OVS DPDK as an example. Right? But you can do other usages. Yeah, you can build a switch, but you can have, any stateful devices also, right? You can build a firewall, you can build a NAT, a VPN, right? You can do a smart NIC. Actually, this is how BESS started as a smart NIC. Again, trying to add functionality as it appears, new functionality, service function chaining, VXLAN, V2, V3, V4, right? It's not available in hardware. How can we add this in software and emulate or simulate the functionality? So that's some of the feature we wanted to provide with BESS. So what have been our use case with BESS? We had a couple of use cases. One of them is this E2. We call this, Elastic Edge. It's one of the ongoing projects at Berkeley, right? You have this E2 controller, and the BESS switch basically is, acting as a virtual switch here on the platform or across a cluster of platform, right? And the traffic, is being spread across the VM. Another usage model, we recently integrated BESS into what we called CORD, Central Office re-architected as data center, which has been run by ON Lab and ONOS. The first integration has been through RCORD, residential CORD. And again here, today the only vSwitch being orchestrated by CORD has been OVS. Using BESS, we saw over 11, 12 times the performance you can achieve with the current vSwitch. So, what are some of these performance, with the BESS software? For packet buffer allocation, deallocation, we have about 10 cycles per packet. The scheduler, CPU scheduling, is about again 50 cycles per round. And we'll go into some of these details, as you'll see the detailed architecture of BESS, right? We have also per packet metadata attribute, right? And with zero instruction overhead for access. Again, we try to optimize as much as possible with the cache line access, right? So, what kind of performance do we achieve with a soft switch? So we went with, OPNAV VSPerf, and we'll measure, phi to phi, 5 to VM phi, and the bunny here, phi, VM, switch, VM, down to phi, right? So 3 of the usage model where performance is being measured by OPNAV. This is the system configuration. So phi to phi performance, and you can see, on the graph that with 2 core and 2 thread, we achieve line rate at 40 gig. And you can also see that about, over 2 times the performance you can achieve today with OVS DPDK, right? We did, do also try to show a comparative chart about some of the other virtual switches that you have out there, right? And here it's just acting as a patch panel, basically, port in, port out. You can see BESS, over 40 million packets per second. We know vanilla DPDK can achieve about 60 million per core, or close to 60 million per core. OVS DPDK also is about 15 to 17. Thomas VPP and the M switch is one of Luigi Rizzo NetMap switch, basically some of Luigi's work. What about, this seems to be the old slide, but well, okay. What about also, phi NF 5 performance? You see, the graph at the bottom, we achieve, line rate at 256 bytes here, and also here with, 2 core, 2 thread per core, right? Let me jump. These are some of the old slides we had, but it's okay. We also show here, some of the core scalability, right? And, either on the top left, aggregate switching when you go from the phi to phi, and as you add, core, and you can see that we scale, fairly well, right? So, we can go through the detail of some of these charts. what about the latency that you have to pay to go through the framework? So when we go, machine to machine, you can see that we achieve, about 8.22 microsecond latency, right? It's just, a ping and send me back the packet. Adding the BESS framework in between, you can see that we just, increase about 0.6 microsecond worth of latency, which is about, a quart for each time you traverse the BESS framework, going up, down, 2 times on each side, right? So you can see that, the overhead of the framework is very, very limited. So performance data here has been measured with, basically 1 flow per port. It should be noted that the framework itself is agnostic to the number of flows. You can have millions of flows. It's not going to change anything. Of course, the module implementing the functionality will be impacted. You need to make some lookup depending upon what you do, right? But the overhead of the framework to carry flows is totally agnostic to the number of flows, right? So now we'll go into the details of what's inside BESS, right? And Sangjin from UC Berkeley will take over.
Thank you, Christian. Yeah, let me start with some brief introduction to the BESS architecture. So let's pretend that this box here is the BESS daemon. It completely runs in user space and just like any other TPDK applications. Typically, it runs on a single core, but you can specify what and how many cores the BESS should run at runtime. So everything is configurable. And at the foundational BESS architecture, there is a driver layer. So obviously, it supports TPDK PMD, or it can also work with legacy device drivers using Linux kernel level driver. And for the virtual port side, it supports many different kinds of virtual ports as well. Obviously, it supports TPDK vhost, and it also supports virtual port for host or container kernel level stack. Or if you really want high performance and if you really fully trust virtual network function, then you can use zero copy interface as well. And all those ports are internally interconnected with something called modules. So you combine multiple modules in a single data flow graph. So what the Datapath does is completely up to you. It's completely up to how you design and combine those modules into a graph. So it's in that sense, it's somewhat similar to VPP. And every aspect of BESS is controllable externally. So here we have BESS controller, and the BESS controller can say what kind of drivers, what kind of ports, what kind of modules should be used running on what cores and what QS policies. So everything is controlled by the external controller with some API. So apparently where the font is broken, where it's so tiny, my apologies. So if you are familiar with the click, then you will find much similarity or BESS data path to the click modular router. So basically, the idea is you compose modules to implement your own data path. Each module is a basic packet processing code. So actually, the BESS framework itself doesn't dictate how big or how small each module should be, but for example, each can be a flow table, for example, or some filter or some load balancer module. And each where I'd say it's fairly easy to develop, implement a new module. So say if I have 5 minutes, then I can say implement a module that filters out all say TCP package, for example. So here we have a list of modules that are built in BESS. So and you can use those modules with your own modules to implement your own Datapath. So one example is say BPF filter. So you can specify some rules like TCP port 80 should match. If packet matches to this filter, then the next module should be this, something like that. And it's blazingly fast. The BPF filter is done with just-in-time compilation. So your TCP dump style filter is going to be translated into native x86 instructions. So you can match package up to 100 million packets per second on a single core. And BESS also has lots of highly optimized match tables like exact match and wildcard matches. So in terms of expressiveness, it's a superset of, say, OpenFlow protocol. There are many other interesting modules. So here we have a simple example that implements a layer 4 switch. So suppose we want to load balance package. If it's HTTP, then first it checks whether packet is HTTP. Then we apply some layer 4 hash with 5 tuples, and after that we replace the virtual IP address with real backend IP address. Another interesting feature of BESS is dynamic packet metadata. So in BESS, each module can tag some metadata attributes to package, and all those metadata attributes are dynamic. So you don't need to say recompile the framework whenever you add new metadata attributes. It can be done dynamically. So you can think of it as some key value table attached to each packet. So typical and traditional way to implement metadata is basically you have a small, say, memory area buffer, and you decide, say, this amount of bytes should be used for this metadata, and this byte should be that metadata. And that is very first error prone. So say multiple modules may use the same offset of the array for different metadata attributes. Then in terms of correctness, it's a disaster. So the other way to implement packet metadata would be, say, you add a field in the packet buffer. So say in Linux, the packet buffer is skbuff. In TPDK, it's RTMBuff. And the problem is that as your protocol stack grows and grows, then you're going to have lots of metadata attributes. For example, in Linux, each skbuff carries like 10 cache lines of metadata data, whether you actually use them or not. BESS has dynamic packet metadata, which has 0 instruction overhead in terms of access. And you don't need to decide what offset should be used for each metadata attribute. It's everything is dynamically computed at runtime. So you don't need to even rebuild the system to implement modules. So this dynamic packing metadata is the mechanism that multiple modules can collaborate together. So each module implementation can be highly decoupled and coherent rather than being end up a giant module as in other frameworks. Another interesting feature of BESS is its CPU scheduler. So well, BESS is a platform for software switch. So in traditional hardware switch, the only shared resource is network link bandwidth. And where if the hardware, the silicon was provisioned enough, then you always guaranteed the line rate performance. But in software switch, you need to care about the link bandwidth and also the CPU cycle itself, because CPU is the limited resource as well. So let me explain what I mean by resource-aware CPU scheduler. So for example, suppose I have this pipeline, and I can declare, say, this portion of the data path should run on core 0, and that portion of the data path should run on core 1. Or I can specify some strict priority so that, say, this port should have strictly higher priority than that the other port. Or I can limit the resource usage of each module or some subset of the data path graph. So say I can limit the resource by, say, number of package or number of bits. Or I can specify, say, this tenant should not consume, say, 30%, should not consume more than 30% of CPU cycles. So you have full control over not only link bandwidth, but also CPU usage. And all those configurations can be combined together. All the priority or weighted share, that things can be combined together in a hierarchical manner. And next, I'll explain about BESS control architecture. So the BESS daemon, the BESS daemon here is responsible for processing data paths, and there is a Python binding that talks to the daemon, and the interface here is something like JSON. What I mean by something like JSON is that it's, in terms of expressiveness, it's JSON, but it's binary format, unlike JSON for high performance. And so here we provide a BESS control, BESS controller, so that you can control the BESS daemon with CLI or some configuration language. I show you what I mean by that. And so, so what you can do with BESS is implementing your own agent here, and optionally you may have some global controller, and this northbound API can be anything. So for example, as Christian mentioned, one of our use cases was, well, translating OpenFlow messages into BESS data paths. So it's a example of the BESS configuration language. So basically it's Python code with some syntax extension for to specify the data path. And then you can see what's the result of the pipeline with the CLI. So BESS Kernel comes with a Cisco-like CLI with all the convenient features like auto-completion. And there are many features that are meant to be developer-friendly. For example, you can inspect say what packets are flowing between modules, or you can inspect, say, how many CPU cycles are being used for each traffic class, etc. So the BESS controller can control every aspect of the BESS data path. It can, say, for example, initialize ports, or it can initialize module at runtime and how to connect them. And it can talk to individual modules. So for example, if the module is a flow table, then you can update the table. Or you can monitor some statistics from ports or modules. So let us wrap up. So BESS is a programmable platform for NFV. So out of the box, BESS is not a virtual switch despite its name. It's a empty playground, and you can implement your own data path with all the data building blocks. It has high performance, or in other words, it has very minimum framework overhead in terms of throughput and latency. And it's fully flexible and extensible. So it's obviously open source, so you can give it a try. It's released on the BSD3 license because I'm from Berkeley, and it has a small code base. So you can take a look and probably understand every aspect of BESS easily. It supports, it runs on Linux 3 and 4, and it supports DPTK 1607 as of yesterday. And it supports QEMU and Docker containers as well. Thank you. And I'd be happy to take questions.
This is a dumb question, but because you talked about modules and flexibility of creating new modules, has anyone come to you asking for storage-oriented modules?
Storage-oriented modules. Could you elaborate a little bit more?
I'm saying it because there are newer protocols. There is an effort to do software-defined storage. There is those new protocols run on things like Fabrics, which runs, one of those is Ethernet. And therefore, there is, at least in my mind, an idea that some portion of the controllers which are controlling DRAM, SSD, and other types of memory functions could actually reside in a controller and go through a data path through the modules that you are describing. I said it is a dumb question because it hasn't been.
No, it's not a dumb question. I'm just
Today we didn't have such a request yet. Yeah.
But because each module is basically stateful and it can store its own state, it's pretty much capable of implementing any kind of functionality in theory. Yeah.
Does BSS needs DPDK to achieve this level of performance, or it can achieve it without DPDK?
So you mean DPDK is the strict requirement for running BESS?
So BSS needs DPDK to achieve the level of performance that you just talked about. You need DPDK.
Some of the performance is achieved with DPDK. You can run also BESS on top of native Linux as you have it, and you're not gonna achieve the same level of performance.
So you need DPDK.
Yeah.
If you want to achieve the performance, yes.
Yeah, for example, for PMD driver, we heavily rely on PMD driver in DPDK. Also, we use other functionality from DPDK, such as IP lookup, for example. Yeah.
Hello. Yeah. So you had different modules, right? And looks like they are spread amongst different cores.
Mm-hmm.
So did you, in your tests, did you find any gains by having more of a run to completion module on a single thread versus pipelining them, the architecture?
Okay, first, BESS supports both models. So depending on how you configure the Datapath, so for example, you can put a queue between cores so that things can be done in a pipelined manner, or you can do run to completion as well. And in terms of performance, it's it depends on the cases. So for example, if you wanna do say 40 gig forwarding, but if you don't want any kind of packet reordering, then probably core pipelining is the only way you can do that. But if you want more better resource utilization, probably it's a better idea to duplicate the pipeline for cores. And BESS provides a mechanism to do both of them, and it doesn't dictate how it should work.
And some workloads also forces you to use pipeline, right? Because you cannot do enough on one core. You have to go through multiple cores, and you have to go through rings in between.
Right. So we have to balance the cost of kind of re-getting the metadata, right, as you traverse the course.
Yeah.
Yeah. Okay. Yeah.
Hi. Very quick question. So all of your numbers with VMs, are they with 0 packet loss or 0.01 packet loss?
It's with 0 packet loss, right? I think. Yeah, 0 packet loss.
0.0, and you're using the vhost user, no patch.
Right.
Huh?
I'm asking, a network pod group running the test over there, but yeah, it's 0 packet loss, with XIA, whatever the XIA defines. Yeah.
Okay, thanks.
Okay, there are no more questions. Well, maybe we can go for lunch.